So now we want to take a look at this technique for solving non-homogeneous equations. Your textbook author refers to this as method of educated guess. As you can see, I have shortened that to just good guessing. So it's a two-step process. We need to solve the corresponding homogeneous equation. That just means taking the non-homogeneous component out and replacing it with a zero, and then solving that. And then we need to guess a solution. And that's what we want to focus on in the next little while, is how to go about guessing a solution. Now here's kind of a summary of what we're going to be taking a look at. The different things that we might see for the non-homogeneous component, here referred to as g of x, are, number one, we might have something involving e to the x. Number two, we might have something involving either sine or cosine of x, or both. And number three, we might have something involving polynomials, such as x squared, x cubed, x, or just constants. And so here is the idea. You can see the way I worded this is try. Now, I'm going to show you how, when we try that, we will know if we have come out with an appropriate solution. But anyway, we'll write these down, and I'll show you how the good guessing works. So, for example, in this first one, since there's an e to the 2x, we would see if our particular solution could be written as something e to the 2x. In the second one, since there's an x squared, we would try our particular solution as being something involving x squared. Now we need to make provision for that being a polynomial, which means along with the x squared we would have an x and a constant. In the bottom one, we would want to make provisions for not only there being a cosine, but a sine involved in the solution. And then there will be times when we may need to combine some of those together. For example, if you take a look at what all this says, it's just basically telling us you need to take the components that we just talked about and maybe include all of them together as factors. So let me show you how this works for a few different combinations. Notice in this first one we've got 25x and we've got a cosine of 2x. If the 25x had been all there was as our non-homogeneous component, that would suggest that we use an ax plus b. If the cosine of 2x had been the only non-homogeneous component, we would have used an a cosine 2x and a b sine 2x. Well, what we're going to do is simply put these two together and have this. Now notice here we've got the cosine 2x and the sine 2x. They each have coefficients here that could be different, and we make provision in those for the ax plus b and cx plus d. On the second one, since we have an x squared and an e to the 3x, we would have the polynomial ax squared plus bx plus c and the e to the 3x. In the next one, since we have an e to the 2x and a sine of x, again, anytime we have a sine or cosine, we have to make provisions for both, because when you do derivatives of sines, you get cosines, and derivative of cosines, you get sines, so it could be that both of those were in the original. However, just like before, we incorporate the e's along with the sines and cosines, and then the constants is what we will need to figure out. And then finally, for the last one, we have all three components here. We've got a polynomial, 6x. We got the exponential e to the x. And then we got the trig function, sine of x. So again, we have to have two separate terms, one with the sine of x, one with the cosine of x, both with an e to the x, and then the coefficients. Well, that would be an ax plus b and a cx plus d. So this screen is just outlining our process that we're about to use numerous times. You might want to again print this page out for your notebook. So let's take the differential equation with the non-homogeneous component 52e to the 2x and see how this works. Well, we solved the homogeneous equation, which has the characteristic equation r squared plus 9, which has solutions plus and minus 3i. Meaning the solution to the homogeneous equation would be the constant cosine 3x plus the constant sine 3x. Since there's no real term, that would be a 0. And so now we want to find a particular solution. That's what we just went through. Our guess is that it's going to look like this, ae to the 2x. We need to find the a. We do that by doing the derivatives of yp. So here's the first derivative and the second derivative. We plug those into our equation and then do the algebra like we did in the previous chapter to figure out what this needs to be. Well, the 13a equals 52 tells us a needs to be a 4. So that would be a particular solution with the assumption that it looks like ae to the 2x. And it does indeed come out to be a 4e to the 2x. So then we write our answer by combining yp and yh together. Now in this example, I'm going to use the same left-hand side, which of course has the same homogeneous solutions. So I'm getting those out of the way. That's not an issue. The issue is how do we come up with the particular solutions by good guessing. Well, hopefully you can recognize the good guessing on this one. Our particular solution needs to be an a cosine 2x plus b sine 2x. We do the derivative of that and the second derivative, plug all of that into our equation and simplify. Well, when we get it down to here, we can recognize from this one that the coefficient of cosine 2x on the left must be equal to the coefficient of cosine 2x on the right. So 5a has got to be equal to 10. Likewise, the coefficient of the sine 2x has got to match. So we set those equal to each other and solve for those. And that gives us our particular solution. So now all that's left is to take the solution from number 1 and the solution here from number 2 and just put those together and call that our solution. Now again, the same left-hand side means we would have the same homogeneous solutions as the previous problem. So we'll get that out of the way. And our guess for this one, since we have an x squared, would be ax squared plus bx plus c. We'll do the derivative and second derivative. We'll plug those into the original differential equation, simplify the left side, and then again simply notice, like in the previous example, that on the right hand side we have an x squared with a coefficient of 81. On the left hand side we have an x squared with a coefficient of 9a. So the only way these are going to be equal is for 9a to be equal to 81. And also, we have on the left-hand side a x with a coefficient of 9b. While on the right-hand side, there's no x, meaning the coefficient is 0. So 9b has to be a 0. And the remaining terms, which are all constant, likewise has to be equal to 0. And so, when we solve these, in the first one, if 9a is equal to 81, then a has to be equal to 9. Second one, b has to be equal to 0. And since we've already found a, in the third one, we've got 2 times 9 plus 9c equals 0, which gives c equals negative 2. So here is our particular solution. We take that and the answer from number 1, put them together, and we've got our general solution. Now in this one, our non-homogeneous component has both an x and an e to the 2x. So let's go ahead and get the first part out of the way. Again, this is the homogeneous equation that we've had in every example so far, which has this solution. And so we recognize that when we've got an x, e to the 2x, we should have a solution that looks something like this. Likewise, with the previous ones, we do the derivative and second derivative. I'll give you time to digest that. You can always pause the video if you need to. We plug those back into the original, simplify the left-hand side, and notice when we divide out the e to the 2x, we get 39x, so the x, which we see here, has to have matching coefficients. So 13a has to be equal to 39. And the constants have to be equal to 0. Now we need to solve those two. The first one, 13a equals 39, suggests that a is equal to 3. We plug that into the second one, and we get b equals negative 12/13. So here's our particular solution, which we combine with number 1 to get our general solution.